All right, so our next topic here is compound probability. We're going to do just a little bit of a warm-up for those of you who missed homework take-up, because what we did last class with tree diagrams and coming up with the total amount of outcomes is going to be important today. And so I got in a situation here where a marathon has 3 scattered starting times, each called a wave. Each wave then has 5 starting areas called corrals, which is true. They do this for the New York Marathon and the Boston Marathon. Well, I think they have quite a few of them now that runners are grouped into. Draw a tree diagram that shows the possible waves and corrals a runner could be assigned to. And so here's on the outside here on the left, it's kind of a more better way of explaining it. All right, so you have 3 different waves, which could be your A, B, or C. So that's your time to start. All right, now from those 3 different waves, because I can't start everybody at the same time. I believe somebody I know who ran the Boston Marathon was like in wave 26 or something, or corral 26. If you're the best in the world, you get rate A1. Now, if you're in A, in this case, you would have a chance to be going between 1, 2, 3, 4, and 5. Same thing with B. If you're in wave B, you can go in 1, 2. No problem. It happens. 3, 4, and 5. And same thing here with C. 1, 2, 3, 4, and there we go, 5. Okay. Now, how many different ways, wave and corral assignments are there? Well, again, this is something we dealt with last class where we have 3 options at the beginning, right, of different waves. And then after that, you have 5 different options of the corrals. And so 3 times 5 is 15. All right, and B, if waves and corrals are randomly assigned, which they are not in real life, but say they are, find the probability that you're in wave B and yet in corral 5. Well, there is only one way that can happen. And so the probability would be 1 over 15. 1 out of 15 chance that happens. Now, again, as a percent, I take 1 divided by 5, or 1 divided by 15, and then times it by 100%, and there's a 6.67% chance that that would happen. All right, so that's a probability, so what we looked at last class. Now, continuing that, because we're going to look at compound probabilities, and we're going to look at 2 different types of compound probabilities. But the first thing is what a compound event is. Compound's a problem because it's the probability. Whoa, 2 big letters there. It is the probability of 2 or more simple events occurring. All right, now there's 2 types of compound events that we're going to look at, and that's independent events, and then the other one that we'll look at, which is dependent events. Now, independent events, independent all by themselves, means the outcome of one event does not affect the outcome of the other event. All right, we'll see the difference here shortly. The probability of 2 events is just found by multiplying the probability of the first event by the probability of the second event. All right, so that's key for us because we're going to use that information. All right, so let's try some examples. So again, we're going to look at compound events. We get 2 or more things happening, but yet they're independent, so they have nothing to do with each other. So we start off with example number 1. What is the probability of rolling a standard die twice, getting an even number, and then a 5? All right, so we have 2 independent events because when you roll a dice, what you get on the first roll has nothing to do with the second roll. You didn't change the dice. You didn't wreck the dice at all. But we have 2 different events here. And again, when I have 2 different events, I'm going to multiply the probabilities. And because our probabilities are generally in fractions to start off, we'll have two different fractions. Now, we're going to roll a dice twice. So the first time there is 6 possible possibilities. And in the second roll, there is 6 possible outcomes. All right, now, the first time we roll the dice, what is the probability of getting an even number? Well, there's 6 numbers, and the numbers 2, 4, and 6 are even. So there's 3 chances of getting an even number. But then we roll the dice again, even though there's 6 outcomes again, there's only 1 chance of getting a 5. All right, now, how do we figure out our compound probability? Well, hopefully you know how to multiply fractions, but if you don't, if there's anything about fractions that's the easiest, it's multiply. Because we just multiply the numerators, the top numbers, so 3 times 1, which is 3. And then we multiply our denominators, which is the 6's. So 6 times 6 is 36. So 3 out of 36 chance. Now, again, as a percentage, 3 divided by 36, then times 100%, I got an 8.33% chance of that occurring. So again, I multiplied my first probability times my second probability. And again, it's easier when it's a fraction because you can multiply the numerators and then the denominators, and you got your fraction. Okay, number 2, a little bit different. What is the probability of tossing a coin 3 times and getting tails each time? So this time we're going to toss the coin 3 times. So we're going to have 1, 2, 3 different fractions. Now, again, they're independent events because when you toss a coin, the next time you toss a coin, it doesn't matter whether you got a heads or a tails the time before. Now, in that tossing a coin, there is 2 outcomes each time you toss that coin. Now, we're looking for a tail on the first one, a tail on the second toss, and a tail on the third toss. So again, finding my probability, I'm going to multiply my 3 fractions. So I'm going to multiply the numerators, the 1s. 1 times 1 times 1 is 1. And then multiply the denominators. 2 times 2 times 2, which is 8. All right, now as a percentage, again, 1 divided by 8 times it by 100%. The odds are getting 12.5% chance of that happening. All right. Next up, number 3. If each spinner to the left is spun once, find each probability. All right. So again, we got 2 different things happening. So I'm going to have 2 different fractions. All right. Now, the first spinner, there is 12 different numbers. So I got 12 possible outcomes. Then the next spinner, I have 1, 2, 3, 4, 5 different colors. So there's my possible outcomes. All right. Now, because of that, I can do that for every question. I'm going to have 12 outcomes, then 5 possible outcomes. 12 possible outcomes times 5. 5 on the bottom there. All right, and then same one here. I got 12 possible outcomes to start, and then 5 possible outcomes. All right, now to figure out our probabilities. So we have the probability of getting an 11. Well, there is only one 11. And then red. There's only one red. Oh, no, wrong. 2 reds. Gotta watch that. All right, so then to figure out my probability, again, multiplying the numerators. So 1 times 2 is 2. 12 times 5 is 60. All right, now to convert that fraction to a percent. So I got 2 divided by 60 times 100%. I got a 3.33% chance of that happening. Not very good. All right. B, to get unshaded, then green. How many unshaded do we have? I'm just going to go numerical here. 1, 2, 3, 4, 5, 6, 7, 8. 8 chances of being unshaded. Then green. There's 2 greens. All right, so then figuring out my probabilities. 8 times 2 is 16. And again, 12 times 5 is 60. Convert that to a percentage. Let's see, 16 divided by 60. And then times it by 100%, I get 26.67%. All right, C, at least a 3, then blue. All right, at least a 3. Well, there's 1, or at least 3. So all the numbers are at least 3 except for 2 of them. So 10 of them are at least 3. Then blue. Well, there's only 1 blue. 10 times 1 is 10. 12 times 5 again is 60. And so, converting that to a percent, we get 16.67%. All right, next up, even and shaded. Ooh, then not red. Okay, even and shaded. How many even and shadeds do we have? We have the 2 and the 8, so there's 2 chances of that happening. All right, then not red. Well, we got blue and 2 greens, so 3 chances of that happening. And so again, let's see here. 2 times 3 is 6. 12 times 5 is 60. And converting that to a percent, let's see here. We have a 10% chance of that occurring. And there we go. All right, number 4, a little bit different. A card is randomly drawn from a standard deck, all right? Then a date in the month of June is chosen at random. All right, so A, find the probability you get an ace and then an odd number. All right, so again, we've got 2 events happening. Now, a standard deck of cards, there are 52 cards. Now, in June, believe it or not, there are 30 days. All right, now, probability-wise, what's the probability you get an ace and then an odd number? Ace, there are 4 of them. Odd numbers, well, if there's 30 days, half of them are even and half of them are odd. So that means 15 are odd. Okay, so we got some big numbers here. Figure out our probability. 4 times 15, I know, is 60. 52 times 30. I got no clue on that one. Let's see here. I end up with 1,560. Now, converting that to a percentage, again, 60 divided by 1,560. All right, then times that by 100%. And I have to 2 decimal places, just a 3.85% chance of that happening. All right, next up. Again, we got 52 chances of pulling our deck of cards, 30 days in June. All right, so now we want to know a probability. The probability that we get a spade. Again, there are 13 spades, 13 clubs, 13 hearts, and 13 diamonds, so there are 13 spades. Then a multiple of 4. How many of those are there? So we got 4, 8, 12, 16, 20, 24, 28. So I got 7 multiples of 4. All right, so again, figuring out probabilities, 13 times 7, I have got no clue on that one. I end up with 91. And then again, 52 times 30 was 1,560. And so to convert that to a percentage, I take my 91, divide it by 1,560. and then multiply it by 100%. And this time, it's slightly better chance of this happening, 5.83% chance. All right. Now, a little something different is what we call dependent events. In dependent events, the outcome of one event affects the outcome of the other. All right. So the probability of two dependent events is found again by multiplying the probability of the first event by the probability of the second event, given that the first event has already occurred. So that's key. That's a little bit different here. All right. So for an example here, we'll do number 7. There are 3 green markers, 6 yellow markers, 4 red markers, and 12 blue markers in a pencil box. A marker is drawn but not replaced. Then another marker is drawn. Find each probability. All right, now to start off, we're going to draw 2 different pencil crayons out of this bag or this pencil box. Now, how many are there? We start off with 3 plus 6, that's 9. Plus 4 is 13. Plus 12 is 25. So we get 25 choices in the beginning. But then you have only 24 because you're pulling one out on the second event. All right. So what's the probability that you pull a red one, then a blue? All right. Well, at the beginning, if you pull a red one, there are 4 possibilities. All right. So you can pull 4 different red ones. And so then you pull one, and maybe you do, maybe you don't. We don't know. But then you get a chance of pulling a blue. And there are 12 different chances that you pull a blue. Now, probability. 4 times 12 is 48. 25 times 24, I have no clue on that one. 24, 600. All right, now converting that to a percentage, I get 48 divided by 600. And then times it by 100%, I get just an 8% chance of that happening. All right, next one. You pull a yellow, then a green. So again, we're got 25 chances, 25 different outcomes. The first pull, only 24 the next. All right, so for green, or for probability of a yellow, how many yellows are there? 6. All right, and then a green. How many greens are there? 3. All right, so again, finding the probability, 6 times 3 is 18. And again, 25 times 24 is 600. As a percentage, again, 18 divided by 600. Not a very good chance here. Times 100%. We get 3% chance of that happening. All right, now we're going to look at something just a little bit different. Same scenario here. Probability they're both blue. All right, so there's 25 pencil crayons. And then 24 left. All right, now here's something that's a little bit different. I'll tell you why. Is both blue. Now there's 12 blue markers. So there's 12 opportunities at first one. But if I pull a blue, there is now 1 less blue. So there would only be 11 blues left if the first one was blue. Because again, these are dependent events. They affect each other. All right, now figure out my probability. Again, on the bottom, 25 times 24 is 600. 12 times 11 is 132. And again, converting that to a percent, I take 132 divided by 600 and then times it by 100%. It's actually a good chance here, 22%. Not bad. All right, our last one, D, probability they're both yellow. So again, there's 25 pencil crayons at the start. After that first pull, now there's only 24. Now, how many yellows do we got? Let's see here. 6 yellows. So there's 6 chances to pull a yellow. And then if you do pull a yellow, well, there's only 5 left on the second pull. All right, now 6 times 5 I know is 30. 25 times 24 is 600. All right, and again, converting that to a percent, what do we got here? There is a 5% chance of that occurring. And there we go. So there is a compound probability. Again, multiplying the probability of the first event by the second event, you have both independent and dependent possibilities. So independent means the things that the experiments, I guess they're called, that you're doing don't affect each other, where dependent events, the two experiments that you're doing, or 3 or more, do affect each other. All right.